doing the inverse for this function, we can't just undo f of x. So here's my f of x. Okay, so there's f of x. I can't just undo this f of x because I don't really know what the calculation is to get this f of x. However, I can do an inverse by just switching the x and y. Okay, so I'm just going to establish some coordinates here. And put those in my table. So -6, -3, -3, +3, 0, +3, +3, -3, and 6, 3. Okay, so what I'm going to do then is I'm going to switch those x's and y's. Okay, so I'm going to end up with all the y's become x's. And all the x's become y's. So when I draw these coordinates, -3, -6, okay, 3, -3, 3, 0, -3, +3, and 3, 6, this then becomes my new function. Okay, so there it is. There's my inverse function. Okay, so this is my inverse of f of x. And I'm going to try doing this. I'm going to try to overlay this on top of the other function here. So I'm just going to copy that. And I'm just going to try pasting it over here. Oops. Okay. I'm just going to grab that again. And if I lay this on top of the other function here, okay, it's taking me a little while to do this, but if I take this function and I overlay it onto this function here, okay, we can see that this is a reflection across that diagonal. Okay, so that blue line is going to be the reflection of the black graph there, and it's a reflection across that diagonal line. So that's a physical property of our inverse functions. So this blue function essentially undid the black function. Okay, so mathematically that's how we look at it. Okay, so let's take a look at the inverse of trig functions. Well, if I take a look at my sine function and I switch the x and y, basically I can just switch the x and y axes and I get the graph that looks like this. Now, it looks a little bit different because I'm missing that other part of the graph there like that. But the problem is in order for the inverse to be a function, it has to pass the vertical line test, which it doesn't when I have those parts in there. So I've got to get rid of those parts. Okay, so I've got to trim this graph to make it the inverse. So there's my arcsine of x. Okay, so my arcsine of x is only defined in this region. So it's got my domain. So the range here is the range, the same range. Okay, so -1 to 1. My domain becomes -1, -1 to 1. Okay, but my domain here was all real numbers. My range cannot be all real numbers, otherwise it's not a function. Okay, so these are not actually perfect inverses of each other either. Okay, so but to make this a function, we need to trim that. So to do that then, we've trimmed it here, and we're essentially going to use this domain. So if I draw my circle in here, okay, so my range is going to be from -π/2 to π/2. Okay, so when I talk about this trig function, the inverse arcsine can only use these angles from here to here. Okay, and that's why when we did arcsine on our calculator, we had to think of theta too, because there were other sine values on the other side of the circle that gave us the same y coordinate or the same sine value. So when we use arcsine for inverses, we always had to remember about theta 2 because of that issue of these are not perfect inverses of each other. So when we look at Arccos, it's the same issue here. Okay, if I flip this over, right, I get this part of the graph doesn't pass the vertical line test. It's not a function, so I have to trim this graph. Okay, so I have to trim the graph so that it looks like that. And here my domain was all real numbers. My range had to be trimmed. Okay, so my range is no longer all real numbers. So my range is only going to be from 0 to pi. Okay, now the domain, the range here was -1 to 1. That was okay, nothing wrong with that. I can just keep that same domain. Okay, see, the range becomes the domain. But the domain had to be trimmed to become the new range because of this issue of making Arccos an actual function. So when we look at Arccos, Arccos is only defined for part of the circle. So we only use Arccos for this part of the circle. It's only defined from here all the way to here. Okay, so there's my Arccos. So the angles I can use for Arccos are only those angles. Now these ones exist as well. That's why we have that theta 2 issue when we solve using the inverse cosine. And then we have this arctan. Okay, so the domain of the arctan was all real numbers except for -pi over 2 to -pi over 2, pi over 2. Periodically we have these asymptotes. But again, we have to trim this function because we can only have one period of this function. So my domain, which becomes my range, then gets trimmed. So it's from pi over 2, -pi over 2, to +pi over 2. But we can include the -pi over 2 and pi over 2 because they are asymptotes. Okay, so they'll never quite reach those points. We can never actually get to those points on the circle. Because when we're at 90 degrees, we have no slope, so we have that vertical asymptote. So the arctan has horizontal asymptotes that look like that. So the domain, the range here was all real numbers. Okay, so the domain here can stay as all real numbers. Okay, so it's going to be from -infinity all the way to +infinity. So we can input any ratio and it will relate to some angle. Now the angles are restricted though, and it's not the whole circle anymore. Okay, so when we talk about the arctan function, the arctan function is only good from -90 degrees, but not including -90, all the way up to pi over 2, and not including pi over 2, okay, because there's an asymptote at that point.